Hello, welcome back. The title of this lesson is called Understanding Probability, Part 1. I'm really excited to teach you this for two reasons. Number one, everybody has experience with probability. I'm going to give you real-life examples that you already understand, so you have some introduction to it already. And number two, the idea of probability is used in all branches of math, science, engineering, all the way into quantum theory is entirely based on probability. It has tons of applications. So what we're going to learn today is something you can grasp because you already kind of understand an idea of what probability is, and it is used for really, really advanced things. So it's something that we're going to use for a long time. All right, so as we talk about probability, I want you to kind of latch on to a couple of things that you have everyday experience with, right? There's a couple of things. Everybody is familiar with flipping a coin, a two-sided coin. Everyone is familiar with a deck of cards, grabbing cards out of a deck of cards. We're going to talk about that a lot. And everybody is familiar with the forecast of the weather, okay? So let's talk about the forecast of the weather for just a minute. We're going to talk about lots of things before we get into calculating probability. But for now, let's just get an idea of what it means. So if the weather person comes on and says, there is a 50% chance of rain tomorrow, right? Then what do you interpret that to mean? Well, it means tomorrow it might rain or it might not rain. You're not totally sure because the percentage is 50%, which means it's right in the middle. But if you instead hear that the probability of rain is 100%, then you know that it will definitely, totally, absolutely rain tomorrow. But if the chance of rain is 0%, then it will definitely not rain tomorrow. If we're right in the middle at 50%, then it might rain or it might not rain, right? So of course, some days when the weather person says 50% chance of rain, some days you go outside, it doesn't rain all day. You say, oh, the weather was wrong, that person was wrong. Or you go outside and a 50% chance of rain day, and it does rain, and you say, oh, I guess they were right. Okay, we have our ideas in our mind about what it means. Let's talk more specifically about what actually a 50% chance of rain means. What it means is if I can make a copy of that day, of all the atmospheric dynamics, the weather patterns, the pressure, the clouds, the moisture content, if I could just like in a computer make a copy of tomorrow's weather situation and make 1,000 copies or 1,000,000 copies, and if I ran a computer simulation 1,000,000 times with the exact same weather, if I could repeat the day, exactly the same orientation of the atoms and the water in the clouds, then on average, about half of those days would rain, and the other half of the days it wouldn't rain. So clearly some of those days it would not rain, and some of those days it would rain because weather is chaotic. The interactions, because we can't model every single molecule in the atmosphere, all we can look is at the aggregate, and we can predict with some sort of percentage probability what's going to happen. So the definition of probability is, if you understand what the probability is as a number, if you could run that situation, we're going to call it an experiment here in just a second. We're going to define that word. But if you could think of it as an experiment where you run the day over and over and over and over again, and you ran it for a large number of times, then as you run it longer and longer number of times, approaching 1,000,000 or 1,000,000,000 times we run the day over and over again, then half of those days are going to rain and the other half will not. That's what 50% chance of rain means. Of course, when you go out the next day and you just run one day of that weather, then of course some days it'll rain and some days it won't. But if you could run the situation 1,000,000 times, then it would rain half the time. If the percentage rain chance is 100%, then that would mean if I ran the simulation 1,000,000 times, it would rain every one of those times. So that is what percentage means. I want you to, probability means, I want you to start thinking about probability as what would happen if I could run this experiment over and over and over again for a large number of times. The probability is telling you how, what fraction of the time then you will get that outcome. In this case, we're talking about rain. So now we're starting to talk about experiments and what's going to happen if we do things over and over again. We need to define some terms in order to understand probability. So let's take a look at our first term. In probability, we talk about the idea of an experiment. An experiment in science is when you go and you pour things in a test tube, or you run, a generator, or whatever it is you're studying, and you see what the outcome is. In probability and statistics, an experiment is just a procedure carried out in order to record the results and test predictions. That's a bunch of words. It just means it's something that we do to see what's going to happen, like flipping a coin or drawing cards. For example, testing if a coin will land on heads or tails. So an experiment is when I would flip one of these coins. That's an experiment. Here's another one. That's an experiment. Here, I'm flipping it again. That's an experiment. Every time you do it, that's an experiment. In our weather example, every time we run the day, if we could run the day over and over again, which we couldn't, but if we could, every day would be an experiment. Now, the trial is just one round of an experiment. So basically an experiment, I guess a better way of saying it is an experiment is how many times you're going to run the trial, I should say. An experiment is, let's say I'm going to flip a coin 10 times. That's a better example. A trial is every single time I flip the coin, and the entire experiment is all of the times that I flip the coin together there. All right, so for example, each time I would flip the coin would be a trial. So I guess a better way of saying it is when I flip the coin, that's a trial, that's a trial, that's a trial. But my entire experiment might be, what would happen if I flip a coin 10 times? I have 10 trials, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Now the outcome is the result of a trial. So every time I flip that coin and it lands on tails, tails is the outcome. So here we go, trial number 1. I flip it, heads. Heads is the outcome, right? Outcome is the result of a trial. Trial number 2, I flip it again, heads comes out. Trial number 3, heads comes out. Trial number 4, tails. That's the outcome for trial number 4. So every time I flip it, that's a trial, and whatever I see that happens at the outcome of that trial is called the outcome. And when you put all the trials together, maybe I'm going to flip the coin 20 times. The entire thing is called an experiment, a procedure carried out in order to record results and test predictions. For example, testing if a coin will land heads or tails half of the time. So maybe I test it by flipping the thing 10 times and see what would happen. I generally expect it to land half the time on heads and half the time on tails. We're going to talk about a lot more why that is the case later. All right, now let's talk about the idea of an event. This one can seem a little bit confusing at first. An event is a collection of outcomes within an experiment. All right, so let's say I flip, the first 3 times I flip the coin, I'm going to flip them 10 times. That's the entire experiment. And the event is a collection of outcomes. So maybe I could say an event would be I get 5 heads in a row, or I could get 6 heads in a row, or I get 3 heads and 2 tails. Any collection of outcomes is just called an event. We just have a word for that. If you talk about the entire experiment and I come and I tell you, hey, I actually got 10 heads in a row, the entire experiment is flipping all the coins to see what's going to happen. And the event is the collection of outcomes that I got 10 in a row, basically. All right, now here is where we make our money here. Probability is the likelihood an event will occur. This is a measure between 0 and 1. We'll talk about that in a minute, and can be expressed as a fraction, a decimal, a ratio, or a percent. Probability, that is what we really have to understand here. So when you're looking at the weather forecast, they always tell you in percentages. It's going to rain, 10% chance of rain tomorrow. You know that means 10 out of 100 times, because that's what a percent is. 10%, 10 out of 100. That's what that means, right? But in probability, usually we express the probability as a fraction, right? 10 out of 100, that's a fraction, right? Or we express it as a decimal, and the decimal is really going to go between 0 and 1. So instead of saying 50%, I might give you the decimal 0.5. 0 is the no probability at all, and 1 is like 100%, and 0.5 is right in the middle at 50%. So I can express any percentage as a decimal. I just move the decimal point back, and so that the range of probability will be between 0 and 1. And the probability in terms of a percent will be between 0 and 100%. So, or you can express it as a fraction. 1/2 is the same as 0.5, but that's also the same as 50%. So you can express these probabilities in different ways. So from the top, an experiment is just something I'm going to test, where I'm going to basically perform multiple trials of an experiment to see what happens. For instance, I have a sock drawer, I have some blue socks and some orange socks, and I know how many of each I have, and the experiment might be, I'm going to pull 50 socks out of the drawer. How many do I expect to get? And so I'm going to test that experiment by performing trials of an experiment. And by trials, I mean I do something and measure the outcome. So the trial could be that I take 1 sock out of the drawer and see what I get. And I take another sock out of the drawer and see what I get. In every single trial, I get an outcome. So I do a trial of an experiment and I get an outcome. And an event is a collection of outcomes. So maybe I observe that I get 5 red socks in a row. That could be an event, right? It's a collection of outcomes that are trials of an experiment, right? And from all of that information, I can then calculate a probability. I can make I can either calculate a probability ahead of time and then check my experiment against the probability, or I could use the data I get to calculate the probability. You get the idea. So I might say that in my sock drawer, there's a 35% chance of getting a red sock on any given draw, because I'm going to teach you how to calculate the probability and what that means. 35% means that less than half of the time, then I should pull a red sock out, and then I might do an experiment to test and see if that is the case. So probability, again, a number expressed between 0 for 0 chance of happening, 1 means definitely will happen. That corresponds to 0% and 100%, but in general, in probability, we use decimals instead of percentages, and we also can use fractions quite a bit. So the entire topic of probability is basically fractions. It's an application of fractions. So that's why we learn fractions first, and you can think of probability as being essentially an application of what you have learned in fractions. All right, so let's start to talk about some different scenarios. So let's say I'm going to flip a coin. We're not going to really calculate anything right here. I'll do a little bit of teaching along the way to kind of help us understand what probability is, but these are just very basic problems. We flip a coin, and of course you have to know that a coin has two sides, heads or tails. What are the possible outcomes? In other words, when you look at the possible outcomes, what could happen? What are the choices of what could happen? Well, the coin only has two sides. It has a side with a head on it, and there's a side that's not the head. We call it the tail side. There's only two possible ways that thing can land. So basically, the possible outcomes are going to be H for heads and T for tails. I'm going to use H for head and T for tails. And I'm going to ask you, are the outcomes equally likely? Now, we haven't talked about how to calculate the probability of something yet. We're going to talk about it in just a minute, and then we're going to have entire lessons on it later. But just think about it. If there's only two ways to get the outcome, there's two outcomes, basically, heads or tails. And the coin is equally balanced. In other words, it's not like lopsided or weighted funny or anything like that. It's called a fair coin, where it can land on either side without having something influencing the way it lands. It's just totally random. And there's only two choices, right? Because there's only two choices and we only have one of each of the two choices, then we expect that half the time will be heads and half the time will be tails. That's something you get when you just play with coins as a kid and kind of from your intuitive experience. There's only two choices, and there's heads or tails, and we only have one of each of those choices, one head or one tail, so we expect that the outcomes are equally likely. We expect that half the time we will get heads and half the time we will get tails. Now, the rest of these problems we're not yet studying all the details of how to calculate probability, but I just can't resist showing you, as we learn these basic ideas, how to generally calculate a probability. So we're going to do it for some basic problems, but just keep in mind that we have entire lessons coming up where we're going to study lots of different situations with probability. So in general, the way we write a probability is it's the outcome that you're looking for in the numerator of the fraction, and on the denominator of the fraction, it's the total possible number of outcomes. So it basically, when you look at calculating the probability, you have to know how many outcomes you have, how many different ways in which the coin could land. The coin can only land in two positions. So the denominator of this fraction is 2. If I'm going to try to find the probability of heads happening, for instance, then first I have to know how many different ways the coin can land. It can land 2 ways, which means the denominator of the fraction of the probability of landing on heads is 2. Now, how many ways in which I can get a heads? I only have 1 heads here, so there's only 1 heads that I can get out of a total of 2 possible ways in which the thing could land. So this is starting to smell like a fraction, right? And so the probability of landing of heads, I'll put probability of heads, is 1/2. And the parentheses, it doesn't mean multiplication, it means probability of landing on heads is 1/2. Why is it 1/2? Because there's only 1 heads that can happen, and there's 2 possible outcomes. That's how you find a probability. First, you have to identify the outcome you're looking for, how many ways that can happen, only 1 heads. And then you have to look at the total number of outcomes in all of the ways in which the thing can land. So there's only 2 outcomes, heads or tails. So because I'm looking for heads, that's only 1 outcome, but the thing can only land 2 ways, that's 2 outcomes. The probability, the fraction of time it'll land on heads is 1 out of 2, 1 out of 2 times. Now, this means 1/2. Now, you all know that 1/2 as a fraction is equal to 0.5. So we can express the probability as the fraction 1/2, right? And we can also express it as the decimal 0.5. Remember, over here in our definition, we said that probability is the likelihood an event will occur. It's a measure between 0 and 1. We got a decimal of 0.5 and can be expressed as a fraction, a decimal, a ratio, or a percent. So we can express this probability in two ways, or more than two ways, really. We can say the probability is 0.5. Remember, the scale is 0 to 1, 0.5 right in the middle. We can also express it as the fraction 1/2. That's okay too. And then if you were looking at the weather or something, what you would do is you would convert this to a percent by multiplying by 100, move the decimal 2 spots, and so it would be 50%. So what we have figured out is that if we flip a coin has two ways in which it can land. The possible outcomes are heads and tails, only two ways in which the thing can land. Are they equally likely? Yes, they are, because we only have two ways in which it can land, and each way it can land only happens one time, so we expect that the number of ways it can land is equally likely. So we put a yes right there. And then just for giggles, even though we haven't gotten to it yet, we calculated the probability of landing on heads as being one possible outcome out of a total of two possible ways it can land, which is a probability of 1/2, which is the same as a probability of 0.5, which is the same as 50% probability that you would see maybe on TV in terms of a percentage. Now let me ask you another question. The probability of heads is 1/2, or 0.5. What's the probability of landing on tails? Probability of tails. It's the same probability, because if you land on tails, there's only one way in which you can get on tails, but there's two possible ways of two possible outcomes total. So again, it's 1 out of 2. So the probability of heads is 1/2, and the probability of tails is also 1/2. And when you put them together, what's 1/2 plus 1/2? The probability of getting either thing, heads or tails, is 1/2 plus 1/2, which is 1. Which means that when you flip the coin, you're guaranteed to get either heads or tails. Because remember, the probability is a number between 0 and 1. The probability of getting heads is 1/2. The probability of getting tails is also 1/2. And if you add those together, you get 1, which means the probability of getting either one of those things is 1, which means you will always get one of those answers. Now, before we go on, what does probability of 1/2 mean in this context? Obviously, I can flip a coin. Sometimes I'll get heads and sometimes I'll get tails. So what does it really mean to get 1/2? All it means is if I flip a coin a large number of times, because probability theory says that the more trials that you do, the more times in which you flip that coin, then the closer and closer the actual observation of heads and tails approach 1/2. So in other words, if I flip a coin 10 times, the probability would tell me that half of those times I should get heads and half of those times I should get tails, 5 and 5. If I flip a coin 10 times, I should get 5 heads and 5 tails. But we all know that if you actually do that, you might not get 5 and 5. You might get like 7 and 3, or you might get 6 and 4. It's not going to be exactly 5 and 5 for only 10 trials. But if you flip the coin 20 times, you would expect 5 heads and 5 tails. It might happen, but you might get maybe 11 heads and 9 tails. They still have to add to 20, right? But as I increase the number of trials, if I go to 1,000 trials, right, then I should expect 500 heads and 500 tails, half and half. That's what the probability is telling me. But I might actually get more like 499 heads and 501 tails. But you see, it's getting closer to half and half. If I run this experiment a trillion times, if I approach infinity number of trials, the more trials I do, the closer and closer I actually expect to see the observation of heads coming up half the time and tails coming up half the time. It's the same with the weather. If I take my day of weather, if the percent chance of rain is 50%, if I could somehow copy the day and run it over and over again for 1,000,000 times, I would expect half of those days to be raining and half of those days to not. I would expect half heads and half tails for this probability if I run it many times, do 1,000 or 1,000,000 trials. And the more trials I do, the closer I expect the probability to match reality. That I'm harping about it because a lot of students can calculate probability, but they don't know what it means. And that's what it means. It means do it a bunch of times, and the more times you do it, the closer what you observe will match what you have calculated. That's what probability is. If I flip the coin 3 times, it doesn't tell me much at all. It's just a number. If I do it 1,000 or 1,000,000 times, it tells me a lot. All right? So let's put this one aside and move on and continue on down the line and learn about some other situations. Let's take a look at problem number 2. Let's say I roll a die. Now a die, when I'm talking about a die, is like for a board game, it's a 6-sided die. On the sides of the die have the little dots, 1, 2, 3, 4, 5, and 6. All right? So I roll a die only one time. What are the possible outcomes if you roll that die? Well, there is no 0 on the die, but there is a 1, there is a 2, there is a 3, there is a 4, there is a 5, and there is a 6. There's only 1, 2, 3, 4, 5, 6 ways in which that thing can land. Each of these numbers, but there is no 0, and there is nothing bigger than 6. There's only 6 sides. Are the outcomes equally likely? Well, I only have one of the number ones. I only have one of these, 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 I only have one of these. So because all of my outcomes only occur one time, are the outcomes equally likely? Yes. Let me ask you a question. If I constructed a new kind of die, let's say I constructed a new kind of die, or I actually modified the die, okay? So normal die has 1, 2, 3, 4, 5, 6 on there. Now let's say that I change it where I put, let's say I change it where I put a 1 on one side, another 1 on another side, another 1 on another side, and then 2, 3, and 4. So in other words, I kind of erase some of the sides. So instead of having 6 unique independent outcomes, one for each side, instead of that, I have a 1, and then on another face, I have another 1, and then on another face, I have another 1, and then I have 2, 3, and 4. Are those outcomes equally likely? Well, I have, you see, 3 sides with the same number. So if I roll that dice, I'm going to expect to get the number 1 more often because there's more sides. So you see, in this case, the outcomes are equally likely because all of the outcomes, they all occur the same number of times. The same thing as here. The outcomes, heads and tails, they only occurred one time each, so we expected the outcomes to be equally likely. We expect the outcomes to be equally likely here because all of the outcomes only occurred one time. But if I modify the die so that I actually make 3 different faces have the same number, then of course I'm going to expect to get that number more often, and the outcomes will not be equally likely. They will not be equally likely because I would expect to get a 3 more often, a 1 more often if I, put 3 faces of the die with the number 1 on there. So that is what I'm talking about by equally likely. You get equal likeliness when all of the outcomes occur the same number of times and none of them is occurring more often. All right. Now, just for giggles again, we're not teaching this yet, but let's see if we can figure out what the probability of rolling the number 1 is. What is the probability of rolling the number 1? Well, what you do is the same as we did up here. For the probability of heads, we first had to identify how many ways in which heads can come up, and then how many total outcomes are there for a trial. So we're going to do the same thing here. How many ways can the number 1 come up? Well, there's only one side with the number 1. So there's only one way in which I can get a number 1 because all the other sides are different numbers, right? Now, how many total outcomes do I have? I have 6 total outcomes. So it's out of a total of 6. It's exactly the same thing we did here. Probability of heads was 1/2 because it was one way of getting a head out of a possible of 2 total outcomes. Here, it's one way of getting a 6 out of a total possible 6 outcomes. So the probability of rolling a number 1 is 6, is 1/6, right? Now, if you take 1 and you divide by 6, you're going to get 0.16 with a repeating bar on the 6, 0.1666666. So the probability between 0 and 1, remember we can express it as a decimal between 0 and 1, is 0.16 repeating, or you can express it as a fraction 1/6, or if you really want to express it as a percentage, multiply by 100, and you'll get 16.6 repeating percent, because don't forget the 6's are going on, so if you move the decimal 2 spots, you'll get 16.6%. So what it means is when you're going to a casino or just playing cards or whatever, if you roll a die, you expect to get a number 1 16.6% of the time, right? So what does that mean, right? What that means is that when I roll the die, I could get whatever I'm going to get. But the percentage or the probability is really telling you that if I roll that die 1,000,000 times, then I would expect with very high accuracy to actually have 16 point whatever percent of the number of rolls that I roll, like 1,000,000 rolls, to actually be landing on the number 1. And the more rolls that I roll the die, the more closely my observations will match with what I'm calculating here. If I only roll the die 1 time, I can get anything. I can get a 5 or a 4 or 1, but I know that as I increase the number of trials, what I observe is going to match what I calculate. Now let me ask you another question. what's the probability of getting a number 3? Well, it's the same thing. There's only one way of getting a 3, but there's 6 total ways in which the die could fall. So the probability is 1/6. What's the probability of getting a 4? It's also 1/6. What's the probability of getting a 5? It's also 1/6. What's the probability of getting a 6? It's also 1/6. Because again, for all of them, there's only one way in which you can get the number, and there's 6 outcomes. What's the probability of getting a 2? 1/6. So you see, we answered, are the outcomes equally likely? Yes. But now we're proving mathematically they're equally likely, because if you get the probability of rolling a 1, or a 2, or a 3, or a 4, or a 5, or a 6, all of the probabilities are the same. They're 1/6. That's why they're equally likely. So from an intuitive point of view, if all of the outcomes only occur once, it's equally likely. But if you can prove it mathematically by calculating the probability of doing that. Now let me ask you a question. The probability of getting a number 1 is 1/6. The probability of getting a number 2 is also 1/6. The probability of getting a number 3 is also 1/6, and on down the line for all of the faces of the die. So what's the probability of getting a number 1, or a number 2, or a number 3, or a number 4, or a number 5, or a number 6? We just add the probabilities. What is, we'll do it right here. What is 1/6? Plus 1/6, plus 1/6, plus 1/6, plus 1/6, plus 1/6. Well, this is the probability of rolling a 1, the probability of rolling a 2, the probability of rolling a 3, the probability of rolling a 4, the probability of rolling a 5, the probability of rolling a 6. We have a common denominator. We keep it. 1 plus 1 plus 1, add those together, you get 6/6. 6/6 is 1. The probability of getting a 1, or a 2, or a 3, or a 4, or a 5, or a 6 is 1. That means 100%. We're guaranteed to get one of these outcomes. When we take all the individual probabilities, they all have to add up to 1. And I've showed you that again up here. The probability of getting 1/2 for this and 1/2 for this, you add them, you get to 1. So when you look at probability, the probabilities of all of the possible outcomes should always add up to 1, because you're guaranteed to get one of those outcomes. And so the probabilities have to add up to 1. You see why I told you in the beginning is that probability is just fractions. It's just literally an application of fractions, and I'm showing you that here. All right, let's go to something a little bit different. We talked about flipping a coin. We've talked about rolling a die. Let's take a look at problem number 3, something a little more complex. You pull a marble out of a bag containing 3 green marbles and 5 red marbles. So you see, this bag has only 3 green marbles, underline this one, and 5 red marbles. All right? So what are the possible outcomes? If I pull just one marble out at random, I'm going to either get green or red, right? Green or red. That's the possible outcomes. So the question is, what is the most likely outcome? Well, you see, you might look at this and say, oh, it's green or red. They're equally likely. But we're hiding a little bit here, because we said there's only 3 green marbles. So in reality, there's only one marble that's green, another marble that's green, and another marble that's green in the bag. But we have 5 red marbles. So we have red, another red, another red, another red, and another red. When we write it all out and we see we have 3 green and 5 red, what do you think is more likely? Well, you have more red marbles. On average, you're going to be pulling red marbles more often. So what is the most likely outcome? Red. A red marble is a more likely outcome. Now, what does that mean? It means that if I have a bag of marbles like this, some green and some red, if I just pull one out, I could get either one. If I pull 2 out, maybe I still get 2 green marbles. Maybe I still get 2 green marbles. But if I do that experiment 1,000 times, right, a large number of trials, then I'm going to expect over 1,000 trials that if I record the results, it's going to be clear that I'm pulling red marbles more often. More often. Because as probability theory says, as I do the experiment, the trial, more and more trials, if I make the experiment have a large number of trials, then the observation I get is going to match what I calculate closer and closer and closer. And speaking of that, let's just take a minute to calculate something and see what we get. All right, let's say that I'm going to calculate the probability of getting a green marble. What is the probability of pulling one of these green marbles out? Well, how did we do it before? We said, well, we have to identify how many ways can I get what I'm looking for? 1 head out of 2 possible outcomes. So here we have to identify a similar sort of thing. How many ways can I get green? Well, you can't really just look at the outcomes. You have to look at how many marbles you actually have in there. I have 3 green marbles in there, right? But how many total marbles do I really have? 1, 2, 3, 4, 5, 6, 7, 8. There's actually 8 of those, all right? So the probability of getting a green marble is the fraction 3/8. Now, consider that 4/8 would be 1/2. That's 50% of the time. 3/8 is less than that. So you know, just from the probability, that the probability of pulling a green marble, probability-wise, is less than 50%. Now let's go the extra mile here and find the probability of, whoops, I kind of messed that up, sorry about that. Let's find the probability of a red marble. Sorry about that, I can't really erase. The probability of getting a red marble. Same kind of thing. How many ways in which can I get red? I have actually 5 red marbles here. And how many altogether? I have 8. So you see, it's the same thing. It's how many ways can I get what I'm looking for in the outcome I'm trying to study, divided by how many total outcomes are there possible. 5 out of 8 here. This one was 3 out of 8. So the probability is 5/8. Now, just for giggles, if you go back and take 5 divided by 8, you're going to get 0.625. Notice again, this is higher than 0.5, so it's more than 50% of the time I expect to get a red marble. And as a percentage, if I multiply by 100, this is moving the decimal 62.5%. So just from the numbers, you can tell that the chances of getting a red marble are higher than 50%. So over the long haul, I expect to be pulling more red marbles than green marbles. And one last thing. What is the probability of a green or a red marble? Well, that's going to be 3/8, the probability of a green, plus the probability of a marble that's red, 5/8. You can add the probabilities. And what do I get? 3 plus 5 is 8. The denominator is 8, and I get an answer of 1. What does that mean? It means that what is the probability of getting a green or a red is 1, because the probabilities have to add to 1. The probabilities of all the outcomes that are possible have to add to 1 because I'm guaranteed to get either a red or a green marble. The probability over here for the, I don't want to crunch my paper up, the probability over there of getting the heads or tails also added to 1, and the probability of the die, also all of the outcomes always added to 1. So the probabilities of all outcomes that are possible in the experiment have to add to 1. All right, let's go over here to number 4. All right, you pull a piece of paper out of a bowl containing 10 slips of paper labeled from 1 to 10. So there are 10 slips of paper. Each one is labeled 1 to 10. What are the possible outcomes? Well, I can get a 1, or a 2, or a 3, or a 4, or a 5, or a 6, or a 7, or an 8, or a 9, or a 10. Why? Because it says I have 10 slips of paper. I have 10 numbers here, and each paper is labeled 1 to 10. So I have 10 pieces of paper. Each paper has a different number on it. Is pulling an even number more likely than an odd number? Well, let's talk about the even numbers. Okay, here's an even number, 2, 4, that's even, 6, 8, 10. So you have to look at what the problem is asking you. Pulling an even number, is it more likely or not? Well, I have 1, 2, 3, 4, 5 even numbers, but I also have 1, 2, 3, 4, 5 odd numbers. Because I have the same number of even numbers as odd numbers, then I'm equally likely to get even or odd, because in the bag, yes, there's a bunch of numbers, but half of them are even and half of them are odd. So I expect that is pulling an even number more likely than an odd number? No. They're equally likely. And let's talk about that for a second, equally likely. Let's figure out what the probability of pulling out an even number actually is. You know, we're going to do these problems a lot later, but let's just kind of do it now. It's not so hard. The probability of getting an even is the number of ways in which I can get an even. There's 5 even numbers here, divided by the total number of outcomes. There's actually 10 outcomes here. So I can get my even number 5 ways, but there's actually 10 pieces of paper in there, 5 out of 10. And when you divide by 5, divide by 5, divide by 5, that's the same as 1/2, which is 0.5, right? So the probability of getting an even is 0.5, which is half of the time. It's exactly what we knew, because we have 5 even and 5 odd. You know half the time we should get even or odd. This is proving it With a probability, I can get an even number 5 ways, but there's a total of 10 papers, and that means the probability of pulling it is 1/2, which is the same as 0.5. Now, here's the next question. What is the probability of drawing an odd number? Well, how many odd numbers are there? 1, 2, 3, 4, 5. Again, 5, but there's still 10 total numbers. So again, 5 out of 10. So the probability of odd is also 1/2, and the probability of even is also 1/2. And when you add all the possible outcome probabilities, you should get 1. 1/2 plus 1/2 is 1. In every one of these examples, the probability, when we calculate all the probabilities that what we can do, and we add them all together, all the ways in which the outcomes can happen, they always have to add to 1, and that is shown here as well. I have one more. Let me take these down, and we'll conquer the last one and wrap up this lesson. All right, here's our very last problem. It says you put all of the dates of the year on slips of paper into a bowl and draw 1. So what are the possible outcomes? You know, I have January 1, January 2, January 3, all the days of the year, all the way through December 31st in there. So the possible outcomes is, I'm just going to put all dates. So there's 365 pieces of paper in general in that bowl, right? And give me an example of an impossible outcome. Well, of course, January 1st, I could pull it out. January 2nd, I could pull that out. January 3rd, I could pull that. Give me an example of a impossible date. How about July 35th? There is no July 35th. That's an impossible outcome. Or you could say something like February 30th. That never happens either. So that's an impossible outcome. So here we didn't calculate anything, but still understanding the possible outcomes and an example of an impossible outcome is important too. For rolling the dice, a 6-sided dice, an impossible outcome might be getting a number 8 coming out. You can't get an 8 on a 6-sided die. That's impossible as well. So here, we've conquered quite a bit. The main thrust of this lesson actually isn't to calculate probabilities. We're going to do a lot of that later, but I just couldn't resist helping you and showing you how to do that as we're learning these basic ideas, because I think it's very, very intuitive for us to understand how to do it. The main thrust is understanding what a trial is, what an experiment is. How do you look at the number of outcomes and to get a feel for, is it equally or not equally likely to get the outcomes? And basically, if the number of ways in which you can get an outcome, if you have a certain number of ways in which something can happen and they all can happen the same number of ways, like heads or tails, there's only 1 heads and 1 tail. On a 6-sided die, there's 6 numbers, but each number only happens once. Then you have equally likely outcomes. But if you change the die and you make it where like 3 sides have the same number, well then things are not like this equally likely anymore. But in all cases, I also showed you, to calculate that probability, you look at how many ways can you get what you're looking for, like heads, divided by, as a fraction, how many total outcomes possible are there? And when you look at the probability of all the different outcomes, all the different things that can happen, when you add all those up, you should always get 1, because then you know that when you do an experiment or a trial, you're going to definitely get 1 of those outcomes. So when you add the probabilities, it's just like adding fractions. They should always add up to 1. Okay, a lot of stuff in there. Let's wrap this up, go through it, make sure you understand. Go on to part 2. We'll continue considering some other scenarios to understand probability.